Okay, worksheet 7. Okay, there's a whole bucket list of things, but worksheet 7, what you should realize is the first few questions are review. You already have the material for that. There is a question that I want you to think about, but I'm not going to tell you what it is. Somewhere in number 1. Okay, so we're going to start now talking about something in number 2, which is a little bit of algebra stunts for typical limit problems. Okay, and so I'm going to put up a problem, and then we'll talk about, let's say, how to do it. Okay, this has a similar format to some of the things on your worksheet. So in this case, what you see is if h is 0, you get a 0 in the numerator and a 0 in the denominator. Always check that, because a lot of times we professors, we just throw easy ones in there to see if you're paying attention. So always check if the thing that you're being asked to take the limit of doesn't have any problems in it. You just compute it. That's easy. Okay. So instead, what we're going to do is we're going to want to expand b plus h. B plus h cubed is like b plus h times b plus h squared. Okay. Now, if you've done these before, you can just skip ahead, obviously. It's a video. You don't have to stay here and listen to me do what you already know how to do. But if you've never done these before, you have to distributively multiply the b over everything. So we have 2b squared h plus h cubed, and then everything times h. So b squared h plus 2bh squared plus h cubed, and then you add all that together. b cubed plus 3b squared h plus 3bh squared. And if you know anything about the Pythagorean theorem, this is all overkill. Okay, but then we're multiplying all that stuff by 7, and then we're subtracting 7b cubed. So obviously the 7b cubed are going to go away. So you're going to rewrite this limit. Just move this guy over, because I don't like him being so far away from his buddy. Okay, just going to rewrite this guy. It's going to be, the 7b cubed is going to go away, but we're going to have 7 outside of 3b squared h plus 3bh squared plus h cubed all over h. And so then what's going to happen is 1h is going to disappear from every piece. All right, now we can let h go to 0. So this is this pattern is you're always going to have stuff minus stuff in the top, and you're going to have like h in the bottom. That's your prototype. That's one of your main prototypes. Stuff minus stuff in the numerator that cancels out at 0, or h is 0. And at this point, you just try to subtract as much as you can, and hopefully everything else that you have in the numerator has an h in it so that you can reduce everything. And the only thing you care about now is this 21b squared is the answer to the whole problem. So that is very, very similar to one of the ones in your worksheet. All right, so here's an example, what I was just talking about before, that if you just say, oh, wait a minute, I can pop 0 into everything, I just get 3 over minus 3, and that's negative 1. So that doesn't require any fancy tools. But let's say we're going to some other limit. For example, I'm pretty sure negative 1 causes a problem, because let's see, in the numerator we get, who cares, and the denominator we get 1 plus 2 minus 3, which is 0, so we have a problem, Houston. Okay, so what we do instead in this situation, we treat it as, well, let's see if we can have a removable discontinuity. We might not get that lucky, but we expect that because it's a typical student problem, so we look for that to happen. We see if the denominator and the numerator can factor. It looks very suspiciously like it should factor, and you factor whichever one is easier for you, and then you say, wait a second, does one of these have a partner down here or not? And it does. Whoa. Okay, there. And so because we never actually reach negative 1, we just take the limit as we get closer to it. That's the rule that allows us to do this cancellation, and then we could put the negative 1 in. 3 minus 1 is 2. Negative 1, negative 3 gives us negative 4 is negative 1/2. And so that's how you do that kind of limit. Again, always check to see if it's safe. If it's safe, then don't do anything fancy, just calculate it. Okay, if you have something like this, this is a setup for the derivative. We're going to be doing this with the definition of the derivative very, very soon. So this is just to help you practice your algebra so that when we get to this on the next lesson, it will be very easy for you. Okay, so what you want to do is just say, okay, I give up. I know that I need common denominators because I'm adding fractions. This always happens. So then you're going to get 4x minus 4x plus h all over h. But that's a lot of writing, right? You can just stick the h right down here and just move this guy over here. And then ask the question, well, what's that numerator going to look like? Well, that numerator is 4x minus 4x minus 4h. And this is the same pattern we were looking at before, in which we're looking for stuff to cancel out so that everything in the numerator has an h in it. So what you're left with is just minus 4h in the numerator. And now, aha, we can get rid of the 4. I don't know why my computer does that. It makes no sense. I got rid of the wrong h, duh. Anyway, this is the h I wanted to get rid of. And so then I get limit as h goes to 0 of minus 4 x plus h, and then now we can finally get rid of the h. Now h can be 0. And there's your limit. Okay, so that's just a really standard type of problem. Now, the next kind of problem, we need to remember something like this. 3 is equal to e to the natural log of 3, or any number. K is e to the natural log of k. That's just what that means. You can prove that to yourself any way you like, but it's a true statement, and once you understand it, it's pretty obvious. But make sure you understand that and believe it. And so then you're going to get some crazy limit like this on your homework that says limit as x goes to infinity of something like, I don't know, like 7 to the x minus 4 and e to the kx plus 18. And so the thing you're supposed to realize is that this 4 and this 18 actually don't mean anything when you're going to infinity. It's just there to confuse you. So you can just ignore those right off. And the question says something like, what values of k will make this infinity like not blow up in your face? All right, so as long as this denominator is essentially larger, it has to be larger than 7 to the x. Because if you want a limit going off to infinity, if something is large and over something that's small, then it will still be large. If you have something that's essentially small over something that's large, this thing goes to 0. So what you're looking for is balance. You want balance, and what you want to do is sort of limit to 1 or some kind of balance. It's not always 1, but you can think of it as being 1. You want some balance. So if e to the kx is somehow equivalent to 7 to the x, well, if k is equal to the natural log of 7, we get that, and then the whole thing balances off, and then it doesn't go to 0, but it also doesn't go to infinity. There's balance, so these things are going to end up canceling each other out. So that's what the problem is asking, if you understand how exponential functions work in that setting. We have something very similar with polynomials. Polynomials going off to infinity. If you have a polynomial of the same degree, like x to some degree, blah, 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 x to some degree, blah, blah, blah. So you could have like 3 over 7, and if n is the highest degree term in that polynomial, the whole limit's going to be 3 over 7. Okay? But if you have something like there's an n plus 1, well, then in that case, this guy suddenly becomes bigger, and then you have small over big, and then that thing is going to go to 0. But if you don't, if you have, like make this one the bigger one, well then this guy is bigger, then this guy goes to infinity. So we're looking for balance. Again, if these powers, the maximum power on your two polynomials is the same, then your limit's going to be 3/7. It's just going to take after the coefficients right there. Okay, and there's lots of ways to prove that. One of the cute ways to prove that, let me just do one out for you, is to say something like, let's say we have 3x cubed plus 4x squared plus 1 and 7x cubed minus 9x, something like that. What you can do is go ahead and divide everything by x cubed on top and bottom. And so then what you do is these things go away entirely and all these things turn into fractions. So you get 4/x over here and you get 1/x cubed. This becomes minus 9/x squared. Then when you go to infinity, then all these pieces drop out. Okay, so that's the easiest way to explain that one. So now you can deal with exponentials that are paired like that. You can deal with, actually you could kind of use that same trick with exponentials, I guess. You could divide out like that. Okay, motion. So if you, we're going to very quickly be getting into like the really guts of this class. We're going to get into derivative definitions and a whole bunch of formulas, and it's going to be a lot of fun. But I want to show you these three graphs. If we have position, we take its derivative, which we're going to be careful how we use that word right now, but we're going to have speed, and the derivative of speed is acceleration. So I want you to just think about the relationship between position and speed as being a little car that's driving along on the road, and the position is just the mile marker, and the speed is your little odometer on your car. And most of them are not little needles anymore, but you probably have been in a car where there's a needle on your odometer. And so I want you to think of that speed as being telling you the change in the position per time. Okay, so for example, if you're going along at a constant speed, then your position graph is going to look like this, and your speed graph is going to look like that, and your acceleration is just going to be 0 down here. Okay, so this is what your position is going to look like, your speed, and your acceleration is way down there at 0. Okay, so this is a constant speed. And I think that makes sense. Most of you have, if you haven't driven a car, you've watched other people drive cars. Okay, now, what happens if I'm accelerating? Okay, for example, I can have a constant acceleration. Whatever speed I'm at, I can accelerate at a constant rate, in which case my acceleration is constant, but non-zero. And then my position is going to look kind of like a parabola. You're going to go faster and faster and faster over time. So that's a way of having constant acceleration. That's going to be what your position graph looks like. And gravity works like this. When something falls due to gravity, it has a constant acceleration. So the speed is increasing linearly and the position looks kind of like a parabola. And that's only if there's no air particles, and we know there's air particles, but your first rough model for a falling object is a parabola. Okay, now what about if you're a car and you're going along at some kind of constant speed and then you throw on your brakes? Okay, so you can't do this perfectly. Let's say you go down like this, right? So maybe your acceleration is nothing, and then suddenly it's like negative. Let's say, I'm going to try to make it, let's see, if you're constant speed, you have no acceleration, and then you suddenly have this negative acceleration, and then let's say you stopped. When you're stopped, you have no acceleration. Okay? What would the position look like? Well, first of all, you're traveling at a constant clip, so you're just going like a line. But as you're slowing down, you're still making forward progress. It's just a lot slower. So let's just say, what do you do later? Your position later is just going to be constant. So maybe let's put this like over here, and then we can smooth this out somehow. Yeah, we can't smooth it out. There we go. We're going to do this kind of thing. All right. because you can slam on your brakes, but your position is going to change more smoothly than your physical reaction of like slamming on the brakes. Okay, so that kind of thing can happen. Let me see what else I want to show you. I guess I'm just looking at the worksheet, and if you had this kind of thing going on, you just had like somebody slammed on the brakes, the way that would look is it would just be like that. That would be crazy. And your acceleration would just be like this little spiky thing. I mean, you can't really do that, but you can do that in a worksheet, so just beware of that. Okay, what else? Also on the worksheet, don't worry about positive and negative. So location, so for example, the diagram is being reused. It says X and Y. I want you to think of this as being position, and this can be time, even though it's labeled as X and Y, because we use a diagram in more than one set of questions. And so you can, it doesn't matter, like there's a 0 here, 0 is irrelevant. Okay, if it's a position graph, where the 0 is, it just is like a 0 mile marker on the highway, and then maybe these ones are one state and these are another state. So like in this state, it's going like mile 1, 2, 3, and this other state mile 1, 2, 3 away from the border. So both states are numbering in the positive direction as they go away from the border. Right, so but it doesn't matter, like it's just a marker on this. It doesn't have any physical meaning that happens to be 0 there. So I wanted to make that sort of clear. Don't make any big deal out of where the 0 is. Okay, I did want to give you another example. I wanted the car to speed up and then go to constant speed. So I wanted it to speed up and then go to constant speed. And so the acceleration is, well, is constant this way and then constant this way. There's a very stylized thing going on. But what would the position of this car be anyway? So we know that if it's going at a constant acceleration, you're still going to get this kind of thing going on. And then you could have, once you reach this slope, you would just continue on at that slope. So that's one possible way of drawing that, but there's other ways that can end up looking. So anyway, there's different ways this can play out. So the thing with those exercises on the homework is I want you to think through them and realize that if a graph flips, it may look different, or if it's stylized a little different, it may look different. So think through what each thing means. Also, another big problem is f is not equal to f prime is not equal to f double prime. This is the big thing to keep in mind when you're learning calculus. One is position, one is velocity, one is acceleration, and students are forever confusing them. So if you're used to a problem like you just did a problem where you were looking at a velocity graph and now you're doing a position graph, you're going to be all confused. So you got to reset your brain each time you have a different problem to make sure you know what you're talking about, and like your graph is going to suddenly look totally different even if it's the same physical situation that you were just talking about. Okay, so I have an exercise for you like this in the worksheet. And I want you to do this numerically. The other ones that are surrounding it, I want you to do algebraically, but this particular one we'll talk about in detail when we talk about limits, when we talk about derivatives. But right now, just for this exercise, I want you to just let h be tiny, let it be 0.1, let it be negative 0.1, let it be 0.0001, let it be negative 0.0, things like this, and see where it's going to, and just where is the number stabilizing numerically. Don't worry about what it is analytically right now. That we will save for some time soon. Okay? So you're going to have questions on the homework that ask you, or the worksheet that say, estimate the derivative at various points. And so you're going to be on graph paper. So what you're looking for is you're looking for, counting the boxes. Okay, so if this is A, then the derivative, if this is F, F prime is approximately equal to 1 because the rise and the run are the same, because you're kind of looking to make like a line between these 2 points nearby. Or for example, if I say, okay, fine, I'm not interested in that point. I'm interested in, let's say, this point right over here, okay? And I think, okay, well, these points are really convenient nearby. This tells me my slope is about minus 1/3 over here. Or what if what I'm interested in is this point? And so I look at these points nearby and I say, well, the slope is about -1/2. That's what we're looking at. We're looking for a visual estimate based on the graph that you're sitting on. If I put a point here and it's a max or a min, then I'm going to estimate that the slope is roughly 0 there. Okay, so that's just should be straightforward, because the question that this is happening on, then the graph is just a 1-by-1 grid, so it's not meant to be really difficult. And while we're talking about that, maybe I should put that graph paper back up. Hold on a second. So if you're doing some kind of visual estimate of the derivative of something, it's nice if you're on graph paper, but you don't always get that luxury, but sometimes you do. So you're going to be asked things like, find the derivative of f and graph it on the same graph paper. Then you're going to say, oh gee, okay, first I'm going to look for where the function is as max or min, and so my derivative has to have a 0 there. So I look for the maxes and mins. And then I say, okay, well, if the thing has a location where it has a maximum slope, like right around here, I have to kind of estimate what the slope is there. So now I have to say, well, is that roughly equal to 1? I'm just going to say it's roughly equal to -1. I'm going to put it down here and say, okay, I'm going to connect this roughly with just, it doesn't have to be perfect. It's good enough like that. But then I say, okay, well, it looks like maybe this thing was going to level off here. Maybe there was going to be a 0 here. And what was going to happen is this looks like it's about the maximum here. Maybe it's a little higher than 1. And I'm going to have another arc that's going to come over like this, but it's never going to reach 0 because I'm going to hit the edge of the page. So it's okay to kind of guess where the curve might be going just to get your artistic bearings a little bit. That's okay. Just don't draw beyond where the curve is actually. And similarly over here, this thing, maybe the next 0 could have been down here. So maybe this guy was thinking to do this kind of thing. But don't go all the way over there, just kind of go like that maybe. Okay, so this would be a decent guess of what f prime looks like. It gets a little bit hairy when you try to do an estimate at f double prime on the same plot, which you're going to have to do for web work. But you just keep going. You say, okay, well, where was the max of f prime? And then that's going to be a 0 in f double prime. If this thing maxed out somewhere, it's going to be a 0 down here. Usually you decrease the number of zeros. So right here, f had just 2 zeros. Well, like I almost kind of am pretending like f had a third 0 here, but I'm not really sure. So if f has 3 zeros, then it's reasonable for f prime to have 2 zeros and f double prime to have 3 zeros. I'm sorry, f prime to have 2 zeros, f double prime to have 1 0 is usually what happens. But this thing looks like it very well may have actually another 0. It's just because I see like this sort of was a max over here, and maybe I need a 0 down here. Okay, but this guy, the f prime was strictly increasing, so if it were the original f, its derivative has to be strictly positive, and it's going to be, all these things are going to basically squeeze closer and closer to the axis, because you're taking a derivative is a process which smooths things out. So maybe like this is probably a maximum on my f prime roughly around here, so that means I need another 0 down here, and so we get this kind of thing going on. Okay, but we have this thing we like to call interlacing zeros, right? So if whatever many zeros, like if f has 3 zeros, we pretend it's got a 0 here, 1, 2, 3 zeros on f, you expect f prime is going to have 2 zeros in between the previous zeros, and definitely f double prime has to have at least 1 0 between the previous zeros. So then you have to kind of guess what to do as you get outside the range of where those zeros were. So the easiest problem in the world is actually the one that looks hardest. The easiest problem in the world is where you just have a whole bunch of zeros on f. So here's the axis, you blah 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 blah, okay? Then you can say, well, that one's easy, because if that's f, then f prime just has 0 0 0 0 0 0 0, and let's say decreasing, increasing, decreasing, increasing, decreasing, increasing, blah blah blah. And then the next one, so that's f prime, and f double prime, you just do the same trick again, but now you pretend like the red function is the first function. It doesn't have to be perfect. And then you do interlacing zeros, so the red function between here and here is increasing, so it's like positive, negative. I feel like I'm missing one here. Yeah, I missed one. Okay, so then you go bing, bing, and so forth. And so that would be f double prime. And again, these guys tend to just keep hugging closer and closer to the axis. It's really hard to draw them that way. So it's okay if you're sketching these, if you draw them bigger than they are. Like you make sort of overemphasize these little humps, because it's really hard to keep them all to scale with them shrinking and shrinking like that. Okay, so numerical derivatives, that's the next task. What if I want to estimate numerical derivative? So for the purposes of this worksheet and for your web work, when you get that kind of question, you deal with the inner points differently from the end points. So what we're going to do is we're going to actually use what's called a forward Newton's difference whatever formula. You know, you can take my numerical computing class and we can talk all about this. But what we're going to do is we're going to sit ourselves at t equals 0, because this is the best we can do, and we're going to do a forward approximation. We're going to do change in y over change in x, or in this case change in f over change in t. It's like we're drawing a little tiny line between these 2 points. So the change in f went up by 1, and the change in t went up by 0.5, so that's just equal to 2. So if we estimate f prime at 2, f prime here rather, it's going to be 2. And we're going to do the same kind of trick on the other endpoint. We're going to just look at the change in f, so we're going to sit ourselves here at the very end point, and we're going to look backwards, so we're going to be backwards. Just a straight old Newton thing. Okay, so we're just going to look and say change in f here as we've gone up by 2, and the t is 0.5, so this derivative we're going to estimate to be 4. Okay, but for all the inside points, we can do better than that. There's something called a 3-point formula. It's so-called 3-point formula, but it only uses 2 points. Go figure. Okay, so it's because we had 3 points to originally look at. You're looking at these 3 points, but you're going to kind of not see this one in the middle, but that's the one that you're focusing on, ironically. So we want to find the derivative at t is equal to 1/2. The best thing that we can do, given our constraints here, if we're only going to look at those 3 points, this makes no sense, but we're going to throw away that middle point. We're going to just calculate using the outside points. So change in y over change in x, okay, same as before. So we've gone up by 3, and the change in t is 1. So we're going to estimate the slope here as being 3. All right, the derivative there. I'm going to do the same thing again for the next block of 3. Again, ignore this guy. And so the change in y, in this case f, is 3. And the change over here is 1. So this derivative we're going to estimate to be 3. And then let's look at this guy. Just keep moving this sliding window. Increased by 3, increased by 1. I didn't mean for it to be so regular. I thought I was making it irregular. My bad. But let's see if this one is. Okay, this one is change in 4 over change in 1. So here we're estimating the derivative to be 4. All right, and now that we've set that up, we can use the same kind of trick to estimate the second derivative simply by assuming that f is now the original, f prime is now the original function, and you can just do that whole trick again. You can say now, wait a minute, just ignore, in your mind, scratch these out, and pretend like those are the f's, and you do this whole same whole process again to get f double prime. Okay, and so I just scratched those out so you can't see them, but obviously they're there. Okay, so hopefully that's enough. I'll just randomly do one in the middle though. What if I want to estimate f double prime at, say, 1? Okay, then what am I going to do? I'm going to look at these 3 points. Well, it's 0. That's pathetic. But let me pick a different one. Let me pick like this guy. Maybe f double prime at 2. So change in y is 1, goes up by 1. Change in x is 1. So the second derivative is just going to be, you're going to estimate it to be 1 there. Okay? Yeah, so I made up pathetic numbers, but that's the process. I guess there's one more thing I didn't tell you. If you have a graph and I tell you this is f prime, how do you find f from that? Well, you need a starting point. So if you don't have any better place to start, you may as well start at the origin, but usually you're given some kind of starting point. So you have to use the same logic you were using before, but it's a little harder because you just can't find the maxes and mins and plant zeros down. But you have to sort of reverse engineer that and say, oh gee, I could go, what? What am I thinking here? How are you going to find f prime? How are you going to find f? So you're gonna look at where f prime is 0, okay, and you're gonna say f prime is 0 there. So that means it's going to be either a max or a min, but in this range, this means my function is decreasing and then increasing. So if I'm decreasing and then increasing, I must have a local min. So I'm going for a minimum point. It may not be the minimum overall, but it's a min right around that region. That's why we call it a local min. And since I keep going up, 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 so like I'm going to be consistently increasing from there on out. So that must mean this min has to occur here, something like this. It's going to occur down below the axis because I have to increase up to 0. All right. There's no more internal maxes or mins because I'm not crossing the axis like that. But what I'm going to get is crazy stuff where I'm consistently increasing, but the rate at which I'm increasing is changing, right? So I'm going to do something like I'm going to increase and then slow down my increase and then increase it again. So I'm going to get weird wiggles, but never mind the wiggles so much. The important part is to know that you're just continually increasing. So you'll be able to figure this out over time. You need to practice, but that's partly what the exercises are there for you to figure out. I will tell you one of the answers to your worksheet though. There's a question that says for this 1 over the positive values of x, 1 over x, what function could you end up with? And I'm going to just say make your life easier, plant a 0 right about here, and then you're going to end up, think about this. I'm going to give you a hint here. I want you to sort of split this up in your mind. There's all these different, here's a region, here's a region, here's a region, here's a region. And think, what regions am I going to be in? Okay? And so I'm trying to get rid of these lines here. Okay, there we go. Now, if I plant my 0 there because it's convenient, and you'll understand why later, if I'm continually increasing, even so the f prime is positive, so I'm continually increasing, what that means is that I'm restricted to be in this box, and I'm restricted to be in this box. That's my clue. Okay, so that's I'm continually increasing, so figure out what that whole thing means, but that will be a start for that exercise, and then try to figure out what the function looks like. Yep, I just double checked the worksheet before I finish my video to make sure that there's nothing I've missed, and I'm pretty sure that I've covered everything I want to cover. There's a couple things I'm leaving for you to think about, but I think you've got enough to go on and that you'll be able to get through the worksheet from this video. So I will see you in class.